Organic Chemistry, Chem 213, Exam 4 Material, Part 3. In this section, we're going to take a closer look at carbonyl alpha substitution reactions. Taking a look at this general structure here, here's our carbonyl group. And as we've learned earlier, one carbon away from the carbonyl group is the alpha position. And I like this graphic because it also displays that the next one over would be beta, then gamma, then delta. And what we're going to look at in this section specifically are these hydrogens on the alpha carbon. That's where we're going to have our carbonyl alpha substitution reactions. These other hydrogens are not acidic. The alpha position, the carbon next to the carbonyl group, is designated as being the alpha position. Here we have our carbonyl carbon. Here's the alpha position. Electrophilic substitution occurs at this position through either an enol or enolate ion. If we look at this graphic going up towards the right, this is the example of an enolate ion being formed. We can see we have a reversible arrow here. In the enolate ion form, our oxygen has the negative charge. It still has its octet. And what was the carbonyl carbon now has a carbon-carbon double bond to the alpha carbon. This is an example of an enolate ion. In this substitution, at this point, an electrophile can come in and it's going to substitute on the alpha position, and the carbonyl group is going to be regenerated. The carbonyl compound can also become an alpha substituted carbonyl compound through an enol. An enol, we've seen this group before when we talked about alcohols. It's when we have a carbon-carbon double bond and an alcohol group. Here we have where our original carbonyl carbon was, and our alpha carbon, we have our carbon-carbon double bond. Up here we have an alcohol group. What makes an enol different than an enolate ion is the hydrogen in our alcohol in our enol is still there, whereas in an enolate ion, the hydrogen isn't there and we have a negative charge. So just as we had with the enolate ion, once we have an enol, an electrophile can come in, and when it comes in, it's going to substitute on the alpha position, and we could get the exact same type of product, an alpha substituted carbonyl compound. Keto-Enol Tautomerism. A carbonyl compound with a hydrogen atom on its carbon rapidly equilibrates with its corresponding enol. Compounds that differ only by the position of a movable proton are called tautomers. The enol tautomer is usually present to a very small extent and cannot be isolated. However, since it is formed rapidly, it can serve as an intermediate. Let's first look at the rapid interconversion of a keto tautomer and an enol tautomer. Keto, we can see that we have a ketone group here. And in an enol, we have our double bond between carbon and our OH group. We have a rapid conversion, and what's moving back and forth would be the alpha hydrogen and the hydrogen on the OH group. What we can see is, with this example of cyclohexanone, that the compound would rather be in its ketone form. And this is showing us that a very small percent of the time is it in its enol form. But just as a reminder, even though it's not formed very much, it can serve as an intermediate. Tautomers are not resonance forms. They are structural isomers of each other. Resonance forms are representations of contributors to a single structure, and the arrow that we use to represent that would be the single shaft arrow with the double arrowhead. When we show this interconversion between these, we have two separate arrows being shown. Tautomers interconvert rapidly while ordinary isomers do not. Here's two ordinary isomers. These are not tautomers of each other. One butene does not convert to a 2-butene. So the difference between ordinary isomers and tautomers are still structural isomers, but they can interconvert to each other rapidly. Again, ordinary isomers cannot. Mechanism of tautomerism. Only the acidic hydrogens are acidic. Acid catalysts. Bronsted acids catalyze Keto-Enol Tautomerism by protonating the carbonyl and activating the alpha proton. Here we have a keto tautomer. Here's our acid, a pair of electrons from the oxygen. In this case, our keto tautomer is acting as a nucleophile, is going to give a pair of electrons to this hydrogen, and a bond will form between this oxygen and this hydrogen. The pair of electrons that were holding our acid together will be given to the anion. Notice we have an equilibrium arrow written here. Now in this piece here, we have resonance. This is the resonance arrow we were just describing. So what's going to happen in this step is we're going to be having these two structures contributing to the one structure. These are resonance structures of each other. We have our oxygen having a positive charge. It has its octet, but oxygen is electronegative and does not like to have a positive charge. So through resonance, it's going to get rid of that extra bond between the carbon and the oxygen. Our carbon is going to become a carbocation. And when it's in this carbocation form, our anion will come in and extract this hydrogen. It'll bond to this hydrogen. The pair of electrons that was between this carbon and our alpha hydrogen will now be given to a carbon-carbon double bond between the carbonyl carbon originally and our alpha position. And we can see again, this is an equilibrium arrow, meaning it can go both in the forward and the reverse direction as written. And we can see that when we have the enol tautomer, we have our carbon-carbon double bond between what was originally the carbonyl carbon and the alpha carbon and our OH. Base catalysis of an enolization. Bronsted bases catalyze the Keto-Enol Tautomerism. The hydrogens on the alpha carbon are weakly acidic and transfer to water is very slow. In the reverse direction, there's also a barrier to the addition of the proton from water to the enolate carbon. Let's take a look at this using a base as a catalyst. Our base piece, in this case an OH, is acting as our nucleophile. It's going to go ahead and bond to the hydrogen, the alpha hydrogen. The pair of electrons that were originally holding our carbon and hydrogen are going to be given to this carbon. And we do have an equilibrium arrow here saying this is reversible. But if it does go in the forward direction as written, we again have the situation of resonance structures. Again, these interconvert back and forth to contribute to each other. Looking at the one on the left, this is a carb anion. The pair of electrons from our carb anion will be given between the carbonyl carbon and the alpha carbon, forming a carbon-carbon double bond. This carbon would have too many electrons when that happens, so a pair of the electrons are going to be given back to this oxygen and we will see the ion being formed. When it is in the ion form, our negative oxygen can then go after a hydrogen on water. So the pair of electrons from this oxygen are going to go ahead and bond to this hydrogen here, and the pair of electrons that was holding this hydrogen and oxygen together will go to this OH group, causing an OH minus. Then again, we have an equilibrium arrow, and our enol tautomer is formed where we have our OH group and our carbon-carbon double bond. Reactivity of enols, the mechanism of alpha-substitution reactions. Enols behave as nucleophiles and react with electrophiles because the double bonds are electron-rich compared to alkenes. Here again, we see the enol tautomer. The pair of electrons on our oxygen is going to be donated to the oxygen-carbon bond. Too many electrons on carbon, so it's going to give a pair of electrons to this carbon here. And what we have in this case is our carbon becomes a carb anion, and it's this carbon right here at the alpha position that is electron-rich. Here we have a carbonyl carbon with an acidic alpha hydrogen. An acid catalyst comes in and it protonates this oxygen here, forming an enol. The enol then goes back and forth during this resonance And when it has a carbocation here, a base can come in, extract that hydrogen, and we can see that the carbonyl group is regenerated and our electrophile is now substituted on the alpha position. Alpha halogenation of aldehydes and ketones. Aldehydes and ketones can be halogenated at their alpha positions by the reaction of chlorine, bromine, or iodine in an acidic solution. Here we have a carbonyl group with its acidic alpha hydrogen. This X is representing one of those halogens we have above. We are showing you an acidic solution, in this case that is acetic acid. And our halogen has been substituted on the alpha position, also giving us a minor secondary product of HX. Halogen isn't involved in the rate limiting step. The rate doesn't depend on the identity of the halogen, but only the ketone and the acid. This is why iodine, which usually doesn't like to undergo these kind of reactions, is able to undergo this reaction. Elimination reactions of alpha bromoketones. Alpha bromoketones are useful in synthesis because they can be dehydrobrominated by base treatment to form an alpha-beta unsaturated ketone. 2-methyl-cyclohexanone will be our example, and we have the reaction we just saw on the previous slide where we're going to have bromo substituted on the alpha position. Now the new piece here is we're going to use pyridine and heat, and what that's going to do is it's going to cause an elimination reaction and a carbon-carbon double bond forming at the alpha-beta position, forming an alpha-beta unsaturated ketone. Alpha bromination of carboxylic acids, the HVZ reaction. Note that we are using carboxylic acids in this reaction. The previous reaction where we had bromo substitute on the alpha position was when we used aldehydes and ketones. This is now we're looking at carboxylic acids. Carboxylic acids don't use the same reagents as we do with aldehydes and ketones. They're brominated by a mixture of Br2 and PBr3. This is a two-step reaction where we would see the first step has Br2, PBr3, and the second step we have water. The end result is on our carboxylic acid, we now have an alpha substituted bromo. Here's an example from your textbook. We have a carboxylic acid. Why don't you go ahead and write out the product, pause the video, and come back and see how you did. We have bromo on our alpha position. Nothing happened to all the other hydrocarbons. It's the alpha hydrogen that is going to be substituted for the bromo. The mechanism of the bromination with a carboxylic acid, here we have our alpha hydrogen, and originally the PBr3 does not attach at the alpha position. PBr3 does a substitution reaction and makes an acid bromide. After the acid bromide is formed, it will convert to an acid bromide enol. After the acid bromide enol is formed, Br2 comes in, and at this point, our alpha position is now going to be substituted, and we will convert the Br back to an OH group using water, so our carboxylic acid piece is regenerated, and we also now have bromo on the alpha position. Acidity of alpha hydrogen atoms, enolate ion formations. Hydrogens alpha to a carbonyl group are weakly acidic. This stability is due to the overlap of a vacant p orbital with the carbonyl p group orbitals, allowing the carbonyl group to stabilize the negative charge through resonance. Looking at this structure here, here's our carbonyl carbon double bond O here. Don't forget this is sp2 hybridized, so it's going to be trigonoplanar. On the alpha position, we have an sp3 hybridized carbon. This is the alpha hydrogen. When the base comes in, we're going to now form an sp2 hybridized alpha carbon. And this, since it's sp2 hybridized here, and our carbonyl group is sp2 hybridized, they're now in the same plane as each other. When they're in the same plane as each other, what can happen is our electrons can then, this is a resonance arrow, go back and forth between the two. The two resonance forms shown are not equivalent. The form with the negative charge on the oxygen is of lower energy, and that's the one shown here on the right-hand side. The reason why this oxygen with the negative charge is lower energy is because it's more electronegative than carbon, and it would prefer to have the negative charge. Reagents for enolate formation. Ketones are weaker acids than the OH of alcohols, so a more powerful base than an alkoxide is needed to form an enolate. Sodium hydride or lithium diisopropyl amide, LDA, are strong enough to form the enolate. What is shown on the bottom of this side is how LDA is formed. Butyl lithium reacts with diisopropyl amine in a THF solvent, tetrahydrofuran solvent, and the lithium diisopropyl amide is formed. Beta dicarbonyls are more acidic. When a hydrogen atom is flanked by two carbonyl groups, its acidity is enhanced. Both carbonyl groups can stabilize the negative charge. Here is an example of that. We have 2,4-pentane dione. We have a carbonyl group to the right and to the left. These two hydrogens here are highly acidic. What makes something an acid is its ability to give up its hydrogen. So when we say these are very acidic hydrogens, what we're really saying is these hydrogens really want to get out of there. Taking a look at the base being introduced, we now have 3 resonance structures. With 3 resonance structures, it's quite stable. The more resonance structures you have, the more stable the molecule. Let's take a look at the flow of electrons starting on this side. When we have our ion, a pair of electrons are now given to the carbon-oxygen bond, causing a carbon-carbon double bond here. The pair of electrons that had the carbon-carbon double bond here are now shifted to this carbon, and we now form the carbanion. The carbanion is not as comfortable with a negative charge as our oxygen is. So what would happen is a pair of electrons would go from this carbon to the carbon as written on the left, causing a carbon-carbon double bond. Too many electrons to this carbon, so it's going to give a pair of have a pair of its electrons go to this oxygen to form this ion. We have 3 resonance structures. The more resonance structures, the more stable the molecule. Now, all these resonance structures are not equivalent. In fact, the one that has the carbon with the negative charge is the least stable, while the ones that have oxygen with the minus charge is more stable. Table 22.1 in your textbook shows acidity constants for some organic compounds. Carboxylic acid has a pKa of 5. An alkane way down at the bottom here has an acidity of 60. Alkanes aren't known to be very good acids at all. These hydrogens don't want to get out of there. But as we work our way up this table, we can start seeing the different acidic hydrogens and the increasing acidity. Reactivity of enolate ions. The carbon atom of an enolate ion is electron-rich and highly reactive towards electrophiles. Enols are not as reactive. Enolates are more useful than enols. Unlike enols, stable solutions of enolates are easily prepared. An enolate ion, here are its 2 resonance forms. We have an electron-rich side on the oxygen here, and when these electrons start moving around, forming this resonance structure, now this carbon is electron-rich. What we can see here is we're going to have 2 reactive sites on our enolate ions. Let's look at the next slide. The alpha-keto carbanion, this is where our carbon has the minus charge, and next to it is a ketone group. And we also have the vanillic alkoxide, where our oxygen has a minus charge and we have a carbon-carbon double bond. These are those 2 resonance structures we saw on the previous slide. Remember, with resonance structures, they're interconverting back and forth to each other, contributing to one structure. They are not going to be isomers of each other. They're the same structure with those electrons flying around. Let's take a look at what happens with the alpha-keto carbanion. The electrophile, when it comes in, is going to cause an alpha-substituted carbonyl compound. On the vinyl side, when the electrophile comes in, we're going to have an enol derivative. The electrophile is now bonded to that oxygen. Halogenation of enolate ions, the haloform reaction. Base-promoted reaction occurs through an enolate ion intermediate. Here's our carbonyl compound and our alpha hydrogen. Sodium hydroxide causes the enolate to be formed. Bromine is substituted on the alpha position. This proceeds rapidly because each halogen added makes the carbonyl compound more reactive. Consequently, polyhalogenated compounds are usually produced. Further reaction, cleavage. In presence of excess base and halogen, a methyl ketone is triply halogenated and then cleaved by a base. This is a methyl ketone. A methyl ketone is when you have a ketone piece and one of the sides only has a methyl there. Because we learned that it's going to be multiply halogenated, in this case triply halogenated, what's going to happen is this CH3 would have had 3 bromines on it, but when the base comes in, what's going to happen is we'll get another oxygen here, and this carbon with its 3 halogens that came in here will now be given off also as a product. This reaction is only useful with methyl ketones, which form HCX3 when reacted with halogens. The HCX3 is a solid and can be identified. Alkylation of enolate ions, putting more carbons on carbon. Alkylation occurs when the nucleophilic enolate ion reacts with the electrophilic tosylate or alkyl halide and displaces the leaving group. This is an SN2 reaction. When we have an SN2 reaction, we have to keep in mind this works best with methyl primary allyl or benzylic. Secondary halides react poorly, and tertiary halides don't react at all because of the competing elimination reaction. Here we have our carb anion. In this case, it's acting as a nucleophile, and it's going to attack our electrophile here. Remember, with an SN2 reaction, it has to have that 180-degree orientation. The pair of electrons that was on this halogen is now going to form an anion, and now we have this carbon attached to the alpha position here. The best alkyl groups for RX, the best leaving group is tosylate, then iodine, bromine, and chlorine. For R groups, the best would be allylic or benzylic, next would be methyl, and then primary. Malonic ester synthesis. This is a way we can prepare carboxylic acids from an alkyl halide, and the net result is our original alkyl halide will have 2 more carbons on it, and we'll be making a carboxylic acid. So when it says lengthening the carbon chain by 2 atoms, the malonic ester synthesis is where these 2 new carbons will come in. This is not the actual reaction. This is just showing us a brief before and after picture. There are slides following giving us more details on this. Formation of enolate and alkylation. Malonic ester, diethyl propane dioate, is easily converted to its enolate ion by reaction with sodium ethoxide in ethanol. The enolate is a good nucleophile that reacts rapidly with alkyl halide to give an alpha-substituted malonic ester. So here we have malonic ester. This is a group you need to add to your list of functional groups that you have to have memorized where you know its structure and name. Let's take a little closer look at this. CO2ET. CO2, that's telling us that we have carbon double bonded oxygen and then an oxygen, and ET is an abbreviation for our ethyl group, which would be the same as a CH2, CH3. So what we're really looking at with this CO2ET is C double bond oxygen. Here's the other oxygen, and this is ET, which is the abbreviation for an ethyl group. So another thing we have with our malonic ester are these 2 hydrogens here. Both of these hydrogens are alpha hydrogens, and because they have a carbonyl group both to the left and to the right, they're especially acidic. So in this reaction, we're going to bring in sodium OET. This ET is also an ethyl group, and ET here is also an ethyl group. This is ethyl alcohol. In this reaction, we get a sodio-malonic ester. One of the alpha hydrogens is now gone. Remember, it's highly acidic. It's able to leave. We form a carbanion, and sodium with a positive charge will be attracted to that carbon with a negative charge. At this step, we can now bring in our halogen, and what will happen is our halogen will be bonded to the carbon that had the negative charge, and now we have an alkylated malonic ester. Dialkylation. The product from the previous slide on that other reaction had one R group attached. Well, it can undergo a second reaction and have a second R group attached. The product still has an acetic alpha hydrogen. Here's our acetic hydrogen right here. It can undergo the exact same reaction, and we can have a second R group attached. In this case, we now have formed a dialkylated malonic ester. Another reaction we can do, in this case, again, it is the single alkylated product. The malonic ester derivative hydrolyzes an acid and loses CO2 to yield a substituted mono acid. So first of all, let's take a look at loses CO2 means decarboxylation. You need to know that decarboxylation means you are losing CO2. It's going to be one of the products. That's exactly what's happening right here, decarboxylation, losing CO2. Our malonic ester, one of our alpha hydrogens, has already been substituted in this example. Under acidic conditions and heat, we are going to convert both this group and this group. In this case, this becomes a hydrogen. In this case, it's no longer an ester, it becomes a carboxylic acid. Where did these ethyl groups go? We get 2 moles of ethyl alcohol as another product. Decarboxylation of beta keto acids. This decarboxylation requires a carbonyl group 2 atoms away from the original acid piece. The second carbonyl permits delocalization of the resulting enol. The reaction can be rationalized by an internal acid-base reaction. Well, we just learned that decarboxylation means we're going to lose a CO2 group. Here we have a beta keto acid. This group right here is our acid piece, our carboxylic acid piece. Right next door to that would be our alpha position. Do you see this has an alpha hydrogen? And next to that would be the beta position, and that's where the keto is. A beta keto acid, the acid piece, and 2 away from that at the beta position is a ketone. When we have this many atoms, it's going to form at one point, because we have a lot of single bonds where rotation can happen. When it becomes planar with itself, what's going to happen is we're going to lose CO2. CO2 is going to leave, and we will form an enol. When we have the enol, the hydrogen on the OH piece of the enol is going to go to the alpha position, and we're going to form a ketone. Preparation of cycloalkane carboxylic acids. 1,4-dibromobutane reacts twice, giving a cyclic product. 3, 4, 5, and 6-membered rings can be prepared this way. This reaction that we have on this slide is going to show us a 5-membered ring. 1,4-dibromobutane. We have carbon-carbon single bond, so we have free rotation. This is going to be our malonic ester coming in its ion form. Our carbanion is going to act as the nucleophile. It's going to attach to this carbon here, and the pair of electrons are going to go to the bromo, so it's going to get out of there. This would be under the conditions also of having our sodium plus and our OET minus in ethanol. Our malonic ester is now going to be attached to this carbon here, and we have the same conditions happening again, and what's going to happen is we're going to now form a second anion, and that anion is going to be attracted to the bromo over here, the pair of electrons going to that. At this point, we are now going to make a ring. We have our malonic ester attached to this carbon. Under the acidic conditions and heat, we're able to convert that to a carboxylic acid. CO2 is also given off as a product, so we have that decarboxylation happening. And we also have 2 moles of ethyl alcohol. When I do this reaction to make sure I can count how many carbons I'm going to have in my ring, notice that our malonic ester is only going to be contributing 1 more carbon to the ring. We started off with 1, 2, 3, 4 carbons, so we will make a 5-membered ring. The malonic ester is unchanging. We're only going to have 1 carbon from that. So it's our starting material here, our dibromo reactant, that is going to lead to the size of the ring here. It'll be 1 more than what we have in our, in this case, butane. If we had a pentane, we'd make a 6-membered ring, and so on. The acetoacidic ester synthesis is used for converting an alkyl halide to a methyl ketone, and this lengthens the carbon chain by 3 atoms. So what we have here is similar to when we had the malonic ester synthesis. There's more detail to it, but this is giving us a brief before and after picture. Our alkyl halide, under these conditions, give us 3 more carbons, 1, 2, 3. As with malonic ester, acetoacetic ester has 2 acidic hydrogens. This starting material right here is our acetoacetic ester. Here's our 2 acidic hydrogens. I have them in blue. These acidic hydrogens are flanked by 2 carbonyl groups, which makes them highly acidic. This is a 2-step reaction where we have our sodium plus, our oxygen with the ethyl group. Coming in would be our R group that we want to add to that. The R group will be substituted where one of the acidic hydrogens was. We can actually have this happen with 2 alkylations, same set of conditions, and now we have those 2 R groups put where the acidic hydrogens were. Generalization, beta-keto esters. Heating in aqueous HCl hydrolyzes the ester and decarboxylates the acid to yield ketone. All beta-keto esters can undergo this type of reaction. The sequence: enolate ion is formed, alkylation, hydrolysis decarboxylation is acceptable to beta-keto esters in general. Cyclic beta-keto esters give 2 substituted cyclohexanones. On our example reaction here, this is a cyclic beta-keto ester. Here's our ester piece here, and beta to that, this is its alpha position. Here's the carbon. Remember, this is a carbonyl carbon. This is its alpha position. This is the beta. So we have on our beta position, we have a keto. That's why it's a beta-keto ester. In this 2-step reaction, again, we see, this is familiar, the sodium plus, OET minus, and we're going to have pH CH2Br. That pH is representing a benzene ring, and because it has a CH2 group to it, it's actually a benzyl. The name of this compound is benzyl bromide. Where the halogen is, in this case, on our benzyl position, that's where the attachment's going to be. Where the acidic hydrogen was here, we're now going to have, this is a carbon right here. This carbon is going to be attached to this carbon here at the alpha position. Under the conditions of acid and heat, this piece right here is going to go away. That's where our decarboxylation is going to happen. And now we have, this is just a rearrangement. All they did was take this drawing and bring it down here. And now we have on this alpha position, we have this R group substituted. It just happens to be a pretty big R group. Direct alkylation of ketones, esters, and nitriles. LDA in a non-protic solvent can be used to convert the above compounds to their enolates. Alkylation of an unsymmetric ketone leads to a mixture of products, but the major product is alkylated at the less hindered position. Here we have a ketone, and to the left of it on the alpha position, I have an R group, a CH3 group. So this alpha position only has 1 acidic hydrogen, and looking at this ketone to the right of it, it has 2 acidic hydrogens in the alpha position. LDA in THF. LDA is a reactant. We saw how it was made earlier in the chapter. The R group in this case is pretty small. It has a good leaving group. We've talked about leaving groups before. Tosylate, iodine are probably the best ones. And what's going to happen in this reaction is the CH3 is going to now be alkylated on the alpha carbon, both sides. The major product is the one that is less hindered. And on this last slide, we can see the direct alkylation of ester and nitrile. Same set of reagents, it's the exact same reaction. What we have here in our ester is our alpha hydrogen is going to have the R group attached to it. And in our nitrile, this is our nitrile group. This is also the alpha position. This is also acidic. And what's going to happen in this reaction is we're going to have our R group substituted where the alpha hydrogen was.